All right, greetings and welcome to today's webinar. Before we get started, I wanted to let everyone know that we will be recording the webinar and we will be sending you a link to the recording after this after the webinar is over. While the phones will remain on mute, we still do encourage your questions, and we'll leave time at the end for Q&A. To ask a question, please type your question into the questions field of the GoToWebinar toolbar. Well, it's time to get started. Today's webinar is a joint presentation by both Intrinsic ID and GlobalSign. Our presenters are James Livinston from Intrinsic ID and Lancen and LaChance from GlobalSign. Both will discuss how the combination of SRAM PUF technology and digital certificates create strong device identities, which is very important for securing the IoT. Our agenda today will start with a quick overview of our two companies and our solutions, a discussion of the IoT security landscape, and then we'll detail how our solutions deliver that important strong device identity. And at the end, we'll take your questions. With that, it's time to get started. Lancen and LaChance will take us through the GlobalSign overview.
Thank you, Christian. I'm Lancen and LaChance, Vice President of Product Management. I work with GlobalSign in building and developing out our high-volume platforms and working very closely in these IoT use cases. GlobalSign's been involved in the PKI and CA industry since 1996 and has been a public CA for a number of years since then. To date, we've issued tens of millions of identities in the public internet, and over the past year, we've invested and built out a next-generation IoT Scalable managed PKI platform. This platform is targeted to scale and build out addressing the IoT scale needs, and we're capable of issuing over 3,000 certificates per second in this platform. We've worked closely with partners like Intrinsic ID to enable strong device identity and address questions of authentication, encryption, and integrity in these connected environments. And this PKI platform and solution is really applicable and addressable in a wide range of use cases, working across enterprise, IoT, and in service provider segments. So I'll hand it to James as well, who will take you through the first part of the presentation here.
My name is James Livinston, Director of Sales for Intrinsic ID, and this is a quick snapshot, our corporate overview. Our main business focus is as the leading provider of digital authentication technology for Internet of Things security. It's kind of a lot to say, but that's as concise as we can bring down our messaging into one sentence. The core technology that we deliver on is SRAM physical unclonable function, both in hardware and in software IP. So when you hear the term SRAM PUF throughout the rest of this presentation, that's what it's referring to. The physical unclonable function based off of SRAM technology. Couple of investors out of Europe, Prime Ventures and Robert Bosch Venture Capital, headquarters in Sunnyvale, R&D center in Eindhoven, founded in 2008. The markets that we serve with our SRAM PUF technology is the Internet of Things, secure transactions, and government and defense. Down along the bottom here, you can kind of see the market traction, both in awards that we've won recently and also in our kind of marquee customers that we're engaged with. Back up to the quote from our CEO, while Facebook connects roughly 1.5 billion people, Intrinsic ID addresses the need for authentication for the Internet of Things, which if you look at the scale of that is expected to connect more than 50 billion devices by 2020. So where you look at Facebook's connection of 1.5 billion people being very impressive, think about each one of those connections have a human behind it, a user and a password for security. We're dealing with security at the level where those 50 billion devices don't have people behind them. A lot of them are machine-to-machine connections. So we're dealing with the authentication of connecting a very large scale of devices. And we'll move into kind of the IoT security landscape now. So if we take a quick look at the IoT security landscape, I've broken this up into a few layers. When we talk about Internet of Things, it starts with the things. So you're dealing with home automation, fitness wearables, smart meters, building access, kind of between the consumer and enterprise space. If you look over at the security standards, there's some basic security functions that are the root for security for these things. Things like biometrics. So if you are using your fingerprint on a mobile device to unlock the device. Identity. So how does it connect to the user and give the user authority to use that device? And also authentication. So how does that device itself connect up through the layers? If we move into the next layer, these things are connecting through gateways. So machine-to-machine, cellular, mesh networks, Wi-Fi. Typically on the consumer side, you see these home gateways that are responsible for the connected devices behind them. In the enterprise space, you see hub and star mesh network types of gateways that then have the authority to give permission to those devices to function. There you're starting to talk about wireless LAN, IPsec, TLS type of connections, and you're also still dealing with the authentication of that gateway up into the next layer that's already there, which is the compute and storage layer. So this is cloud, data centers, server storage, etc. Here you start talking about NAT translation, packet inspection, but you'll also note you still have to then authenticate the data that's passing through the network. Which device did it come from? Which network does it have access to be stored on or delivered to? And then when we look at the top level here, above the compute and storage, is the actual applications, the analytics, the tools, and everything that is making use and delivering services to those things. So we're talking about, if we look again at the fitness and wearables, then maybe secure payments is the application that's running on that watch. So now you're into, again, user and password. You now get to the idea of, can I remove that authority, revocation, but I'm still looking at authentication. So I have to authenticate that user. And if we advance right here, we'll see that the key message throughout all of these layers is the authentication of these devices and services and the people using them. There's a lot of different areas of authentication that our technology and GlobalSign's technology applies to, but for the purpose of this webinar, we're going to look at the connection between the applications and the things. We're not going to worry about the middle layers of the gateways and the compute and storage. That's a whole different topic of conversation, which we'll probably hit you up for another webinar on. But if we move into the next slide and focus on these things, I'm taking just an enterprise application here where we've got a smart meter. The security of things relies on PKI, and that's a good thing. It's been moving towards this. It hasn't even had the concept of PKI before, and now it's moving into this area. So I listed up there, a PKI is a public key infrastructure. It's an arrangement that binds public keys with respective identities of entities. So a public key is something that can be pushed out into the public network and shared to prove the identity of a device. And right now, especially in the industrial IoT space, if we look at the smart meter application, we're just entering the age of PKI for gateway to the application, which is a good move forward because now we are looking at those gateway devices and saying, is there a way to publicly share your identity that I can prove it between your hub and your application? So that's where the application can trust the gateway for the identity of the connected devices. But we can see there's a missing layer. We don't go deep enough with this model, but this model is a good step. The next step brings you up into the middle of the range of security for the Internet of Things, which is allowing the device to have its own identity, bind itself to a public certificate that can be looked at by the application. So now we've made a big step forward. Now that smart meter itself, through the gateway up to the application layer, can be trusted. So applications can now establish trust with the devices directly. That level right there is a very big movement forward. What we address in the deepest layer here, if we move to the next, is the concept of device PKI with SRAM PUF. What this allows us to do is bind that identity to the hardware source inside of that device. So maybe in the medium layer, there might be some serial numbers that are used to prove identity, or there might be some burned keys that are visible in a one-time programmable space that might be vulnerable to a physical attack. If we look at taking the device identity all the way down to the processing unit of that thing and do it with SRAM PUF technology, now we've got the individual devices being able to communicate and authenticate to the applications, but we've added an additional layer that allows the device to prove that it's still genuine. So there's an internal root key that's generated. There's unclonable identities because of the physical unclonable functions. There's keys are protected on the device, and they're deployable across a wide scale of microcontrollers. So this, in our view, is how you build the strongest device identity that then gets wrapped up into this public certificate that allows these devices at the root of their silicon to be able to prove their identity on the network. And as we roll into this next one, this gives you an idea of kind of the process of how you give an identity to a device. If we look over here at an IoT device with general blocks there, that might be inside of a microcontroller, MPU, a CPU, an SoC, ASIC, but they're going to have similar building blocks. And one is they're going to have SRAM. We have not run across a processing unit that doesn't have SRAM available for us, so that's part of the reason our technology can be scaled and delivered so widely. So the first step that we would do is what we call enrollment. The SRAM PUF would generate a unique fingerprint for the device. So that's out of the entropy source on that SRAM, and we're going to get deeper into that as I get into my specific section on SRAM PUF. The next step is from that fingerprint, inside of the chip, we would generate an asymmetric public and private key pair. So it's very important to note that this is all being done inside of the electrical boundary of the chip. So with this public and private key pair generated now, we can move on to the third step, which is pulling that public key out into a provisioning PC. There's lots of ways that this PC can be implemented. Typically, it might be done on a hardware security module, an HSM, but because no secrets are leaving the chip, there's actually the potential of reducing the amount of protection and security that would be needed on this provisioning PC. This would be happening in a manufacturing flow, so typically a contract manufacturer that is building this IoT device. When it's loading the OEM firmware, it would start this process. And then, in the spirit of cooperation, I'm going to turn over the next steps to Lancen.
Great, thanks, James. And so after the provisioning PC receives the public key from the device, the provisioning PC may apply some additional logic or validation prior to making the identity issuance request for the signing of a certificate, but it will send that public key and potentially a device identity into GlobalSign's high-volume CA for signing of a certificate. When our services receives that request, there may be some additional validation based upon the rules or business logic that the environment requires, but we sign and send back from the configured hierarchy a certificate with that unique device identity bound to the public key that was provided to the signing service. And then from there, we through the provisioning PC, and as James mentioned, this is one architectural approach and option in a device identity provisioning. We will receive that certificate and then send it back on to the device for the final provisioning and installation of the identity onto the device in step 6. And the device will receive that identity and store the certificate in flash or whatever storage mechanism. And it has an identity at this point with the keys protected by that SRAM PUF that makes the private key essentially non-exportable from the device, and you create a very, very strong device identity. And so James can go into a bit more detail over the details of SRAM PUF.
Great, thanks. So we will move forward in the slides. So when we look at authenticating everything, and we've been talking about the Internet of Things, I'm back to those things again, the layer there at the very bottom, so the watches, the smartphones. And if you pull back the layer on these, they all have a processing unit inside of them. They have some sort of controller. And our technology allows that hardware level to generate a key. So to start this off, we can provision keys based on the silicon that is unique to each one of these devices. The next step, once you have the key inside of here, now you can start using that key to build the rest of a security subsystem. So if we look on top of these devices before they connect out into the cloud, first thing you might want to look at is verification. And this is where we're talking about certificates. This is where you could use public information to sign the certificate and then be able to use that certificate for whatever type of network it can connect to. On top of that, for some of these devices, you might want to go a step further and generate keys or derive keys from that root key that allows you to have a vault inside of there to store sensitive information. Again, the key for that sensitive information is going to disappear when the SRAM PUF key is gone. So you've got devices, you've got their hardware root, and now you start building up into their connectivity requirements. And in the next slide, we will talk about how that SRAM PUF gets generated. So this is our basic walkthrough of years and years of research and documentation and certification broken down into 4 steps. The first step is all silicon has deep submicron variations. These are variations that happen during the manufacturing process, and they're natural to that device. What we can do is we can look at the process variation in the next step. We did all of the time in the research to look at the best commercially viable source of entropy, and SRAM startup values is where we settled. So when an SRAM transistor is powered up, there's a randomness. It settles on either a 1 or a 0. And the next step, if you take enough of those startup values, you can actually find a highly random and completely repeatable pattern inside of those SRAM cells. That's the core of our technology, is both the ability to read that randomness and then redirect back to a cryptographic key out of that randomness. So in the 4th step, you have the SRAM PUF key, which is generated. So the silicon fingerprint is turned into this cryptographic key, and now you can start to build the rest of your security subsystem. So the advantages of these steps is that SRAM PUF is device unique, it's unclonable, it leverages natural entropy already found in the manufacturing process, does not require any modifications to the silicon, and no key material is programmed. So versus legacy systems that burn a key in, store a key in secure storage, we never have to worry about the secure storage of the key because it is gone at the power off of the SRAM. And what I just talked about in where you store this key, there's some advantages that we have inside of our secure key storage method. If we look at the bottom of this, we've got cost from left to right, we've got security from the bottom to the top. Traditional models of securing keys inside of devices uses ROM fuses, EEPROM, antifuse, and as you see, they start to scale up in cost, they also scale up in security. The challenge with all of those solutions is that they do have the risk of physical attack threat. So the key is programmed externally, typically coming from the outside, then programmed inside. There's also permanent physical alteration, and depending on your level of tools that you have available and your sophistication that you have, the key will be visible in the structure. And it's been proven across all of these methods that with the right amount of time, the right amount of money, you could get in to find that key. If we layer now SRAM PUF onto this, at the very top, highest in security and almost down at the very bottom of cost. Again, because we're not asking for modifications to the silicon. So the keys generated by the device entropy, no traces of sensitive data, and no secrets stored on the chip. So if we look now at how this works inside of a typical SoC, you've got a CPU, you've got some flash, you've got some SRAM, you have a crypto module. I'm assuming that we are going to be concerned about security on this, so you've got some security functions and you've got some maybe a memory protection unit, some other functions that you can lock down and create a trusted environment. we look at the first thing that our technology helps apply here is that the secret key now is generated completely inside of the SoC electrical boundary. So it's chip unique keys that are created at any stage of production. It is not dependent on the silicon manufacturer injecting a key and then shipping those devices out to the contract manufacturing phase, and those keys have seen exposures potentially. The other thing that we add here is we're based on standard SRAM. So again, no modification to the silicon and portable across process nodes. So we've run our technology from 180 nanometer down to 14 nanometer and continue to move. We have very little to no process node dependency. We're a digital architecture, so we scale along with the process nodes. The other thing that we do here is we remove the requirement of the SoC to have one-time programmable storage. So whether that's fuses or protected flash, we do not require that for the storage of the key, because again, the key is on when it's needed, used when it's needed, and then gone when it's not in use. We have two ways that we roll out these products into the field. The first one is QUIDDIKEY. That's our product name for our hardware IP. So this would be delivered as RTL, typically to a semiconductor vendor. So they would buy this product from us, embed it into their design, and then ship it out in production, ready to already enabled or ready for customer enablement. The other way that we can roll out this technology is in BroadKey, which is our software IP. So this would be delivered as libraries. And again, this could be delivered to a silicon manufacturer that wants to have quick delivery to market of SRAM PUF technology, or also a very broad coverage across multiple MCUs that have already been designed and are in production. This can also be delivered then to the device makers themselves directly. So somebody that has 4 or 5 different MCUs inside of their architectures could buy the software IP and lay them across all of the different architectures. One advantage that you have inside of the hardware delivery mechanism is some speed. So you have a dedicated hardware engine for this. You can see this big difference in the cycle speeds between the two. The biggest advantage of BroadKey is its portability, again, across the microcontrollers, CPUs, ASICs, and also the idea that in the field you could actually update your devices. So if you could put your device through an enrollment, a secure enrollment process, you could do this on a smart meter that's already out in the field, say with a technician that was trusted to load it and put it through an enrollment process, and now you've got a security function on that smart meter that you did not deploy it with. And we'll in the next slide, we'll take a look at the key provisioning system. So Citadel is another product from us that takes advantage. If we look at the silicon manufacturing stage, it would use QUIDDIKEY there. So the silicon manufacturer would embed QUIDDIKEY. If then the silicon manufacturer hadn't embedded it, but a device maker in the next stage, in the contract manufacturing stage, could load BroadKey onto that. So either one, you could make it start of the process there. Now what you have is you have a silicon root of trust, root key, that can be used in that private public key pair situation now to get to device unique certificates. So at the contract manufacturing stage, you've now given device personalities unique to each one of those devices. And now out in the field, you'll see up here at the top, the OEM has been managing all of this within our Citadel key provisioning system. So now they have a OEM management tool that allows them to understand how many certificates have been created, what devices they were created on, and then also extend, like we were talking about the bulbs before, maybe give an application key to a music service that wants to be able to lock and unlock the use on an individual device. The OEM can manage the distribution and revocation of those types of application keys. So this is a very quick overview of the start of our SRAM PUF technology all the way out to how it gets pushed out into the field through the manufacturing process. And now we will push this back over to Lancen, where he talks about, now that you have that device identity, how do you do this at scale? So if each one of those individual devices can have their own unique identity created by SRAM PUF, what then can you do in the manufacturing flow for PKI infrastructure?
Great, thanks, James. Yeah, and so one of the points I'd like to start with here is we've gone through at a high level PUF technology, SRAM PUF technology, and PKI, and at a fundamental level they are slightly different in the sense that PKI is a technology that's been employed for the past 20 years or so, and SRAM PUF is a bit newer in the stage. And so what does that really mean for PKI, as far as how does PKI now apply into a larger, more scalable environment? And there's a number of next generation IoT considerations that we look at when we talk about PKI. And so this is applicable to both PKI and SRAM PUF, but really the size, scale, and scope of these ecosystems are really going to drive the architecture and the technologies that you choose and select for securing those environments. How do they scale, and what are the cost implications? On top of it, we definitely see a huge diversity of devices and operating environments. And this is, for PKI, an especially interesting and sticking point for a lot of deployments. That as PKI is deployed in a traditional IT environment, the diversity of those environments is, not so much a concern. There's very broad, or there's a large number of standards, I should say, and common architectural patterns and a consistency in operation environments and software stacks where PKI can be easily consumed. But as we talk about the IoT, these devices are now introducing constraints in their processing power, their connectivity. There's a huge diversity of software stacks and real-time operating systems or embedded operating systems that you need to fold these solutions into. On top of that, we also see in the IoT an evolution of trust models and more complexity in the relationships. That PKI, as it's deployed in its largest use cases today, is really hinged around a public trust model that is centered around trusted CAs like GlobalSign being embedded in connected software and hardware of the existing internet ecosystem. But as we move into IoT scenarios, that there's new requirements that are more closed or more private trust ecosystems. And how does the PKI solution that you're applying into those connected environments really address those new use cases? And then, as James also alluded to, the life cycle of these devices is going to be very unique by use cases. And how and where in these life cycle processes are you going to embed the trust anchors and the trust assumptions that you need to have a successful and trustable operating environment? So these are some of the core tenets that GlobalSign's been looking at in conjunction with our partners over the past few years, and definitely drive the evolution of our solutions here. And as we move into a selection of a architectural or deployment option in PKI, there's really a range of options that architects and implementers do have, especially in the PKI infrastructure. And these range from open source or quote-unquote free deployments to commercial CA software that you run on an owned hardware, to on-site appliances or managed services, into the cloud-based or software as a service model. And the selection of this type of PKI architecture really requires the decision makers to make a trade-off of software costs and hardware costs, the maintenance and labor costs involved, the risks that are being taken on in poor configuration or compromise or misuse of PKI environments. And specifically, as we talk about the scale requirements for IoT ecosystems, what are those SLA needs, or what's the use case requirements for this next level of magnitude? And how does this solution scale as you grow from a proof of concept to an initial production deployment to a large-scale production deployment? And so GlobalSign is a cloud-based PKI provider, and some of the core benefits around operating your PKI system in a cloud-based environment really enables, a couple core bullet points here. So one of the first tenets is a simplified infrastructure and requirement and cost consideration. So really by moving this PKI into the cloud, you don't have the additional hardware and security concerns of an on-premise solution. It reduces this cost, especially in a contract manufacturing environment, as you want to extend to multiple contract manufacturing sites, and that you don't have to duplicate this hardware environment. It's a much lower cost to expand. And it also reduces or eliminates on-site CA infrastructure concerns, that you don't have to worry about the personnel on site potentially compromising or having access to that root material. In addition, as common with a lot of software as a service models, it allows a shift to more elasticity in both expenses and performance. And expenses, we can consider shifting from capital expenditure and hardware and upfront cost into a more operational expense that expands as the solution grows. Conversely, with performance, scaling up from a proof of concept, which a lot of these deployments are really looking at, is the tens or the hundreds of magnitudes of devices, into a production deployment of billions of devices. And you can do all of this with a cloud-based solution for PKI without changing infrastructure hardware. And then on top of it, a cloud-based solution offers a number of capabilities for auditability, access control, and reporting in a very centralized manner. And this also relates back to this consideration for how you expand in a multiple site contract manufacturing environment. And so what GlobalSign's invested in over the past few years is a next generation managed PKI platform that's flexible and scalable to meet the needs of high volume PKI use cases for these Internet of Things ecosystems we're looking at. And some of the core tenets that this platform has been built to service are the volume, the pure number of identities that are being issued, so billions of certificates and identities per ecosystem, and also addressing the concerns and considerations for the enrollment requirements. How do you provision 1 million devices at a very, very high throughput scale? And so these are the core architectural attributes of this next generation platform. And then on top of that, looking at the variety of devices, these diverse chipsets and operating environments that are folding into the usage requirements, as well as the life cycle and flow of these identities and devices. And how do you service your identity solution to meet these needs? And these are the core things that we've done in conjunction with our partners like Intrinsic ID here to address how device identity is being secured from the cloud all the way down to the chipset. So I think with there, I'll just wrap up that GlobalSign and Intrinsic ID are really at a cutting edge here at how we're securing that device identity at a very cost-effective and scalable manner. We're really looking forward to working with organizations at a proof of concept pilot to production level. And we'll open it up to some questions here and transition to Christian.
Great. Thank you so much, Lancen. Thank you so much, James. I think we had a great presentation today. The questions are starting to come in. We do want to remind everyone that if you do have a question, please use the GoToMeeting questions field to ask your question. Our first question revolves around which industry and use cases have you deployed this solution into so far? I'll open this up to both Lancen and James at this point. Lancen, you want to maybe start with this one?
Sure, yeah. So as far as GlobalSign's deployments, we do see a lot of use cases in almost hybrid IoT solutions. And so the early adoptions of PKI in IoT ecosystems are in more gateway type devices. But as we do get into some of the earlier use cases, we are working on spaces within the smart grid and the energy industry, as well as the industrial internet space. Ecosystems where the value and the risk in those assets are much higher, much more applicable for the early adoptions. I know James has a number of use cases too that I'm sure he's itching to talk about as well.
Yeah, thanks. And I will echo the importance of the initial attraction in that industrial IoT space is very high. Again, they understand what security is. They understand that you pay for it. A little different from the consumer space where the idea is it should just be secure and they don't want to add a price on top of that. When we talk about our specific industries and use cases, SRAM PUF for us started off inside of banking and secure transactions space, and also in the government and defense space. From there, we started pushing the technology into anywhere that you can imagine a microcontroller going. So inside of microcontrollers for IoT applications, we're on sensors right now. We're inside of FPGAs. We're being used inside of data centers. We're being used for DRM protection. Again, the government devices, and then also a movement right now is we're starting to move into the connectivity chips. So standalone chips that are Wi-Fi, Bluetooth, other connectivity chips that would actually have the root of trust embedded in the communications module. So that's kind of a wide variety of the use cases and market spaces that we're already deployed in, currently being used in.
Great. Thank you, guys. This next question is definitely geared towards you, James.
Yeah.
How is helper data managed for the QUIDDIKEY and broad key implementations, and where is it stored?
Yeah, great. So for the definition of helper data, this is the information that allows you to get back to that unique, device-unique SRAM PUF key. And this is data that does need to be stored. So it needs to be accessed by the processing unit. So there's a couple of different ways that this can happen. This can be stored in memory, say in flash on chip. It could be stored in memory off chip. There's even applications where it's being stored in the cloud. With all of those methods, the important thing to understand here is that the helper data reveals no information about the secret key. So it is non-sensitive information. So it can be stored in all of those different locations, providing that the processing unit can access it. So it doesn't matter if you do it on the chip directly next to the processing unit, off the chip on the board, or even in a cloud application like I mentioned. So it doesn't leak any information on the secret, and also the helper data has its own built-in integrity check. So that helper data can't be modified outside of the source, pushed back into the processing unit. If there's been modifications to it, then the integrity check will fail, and it'll stop there. There's nothing else that'll be used for.
Great, thanks, James. The questions are rolling in, so keep them coming, guys. It's great, always great to have some interaction going on here. This next one is for Lancen. In the past, we have run into problems when dealing with certificate validations, revocations on smaller MCUs that can't handle the extra CPU cycles needed to do this, and then also trying to layer in a complicated CRL OCSP flow. In a complicated architecture. What do you suggest for folks in implementing thousands of these smaller devices into an IoT system, since PKI is definitely such a strong identity solution that's been around for a long time?
Yeah, it's a really interesting question. It's definitely, one of the, kind of next generation concerns of PKI as it's deployed. And one of the things that we do say a lot of times is that PKI is a information security Swiss Army knife. And the benefit in there is that there's a lot of configuration options on how these ecosystems are being addressed. But so going back to this concern over constrained devices that may not have capabilities for OCSP or CRL, there are, a number of approaches you can take to address this. So one of the components that is especially interesting with this joint solution with Intrinsic ID is where you may arrive at potentially two identity certificates for a device. One that's more around its core identity that might be long-lived, and another that is based upon a shorter duration certificate. And so instead of relying on a OCSP or CRL service to validate that identity of the device, but you might rely upon the authentication or the provisioning of the certificate in a more frequent interval, where you're using shorter duration certificates for the authentication of the device in the environment. That's an approach that we see and we can support, and definitely it's a requirement on why you need a much higher scale ecosystem, because if you're talking about a environment with thousands or hundreds of thousands of identities and provisioning thousands of those certificates per day or per week, that really boosts up the requirements on that infrastructure. There are also other approaches in how the CRL or OCSP services can be configured and deployed. There's other there's lighter weight options that we are investigating and profiling in there too that help reduce some of the bandwidth requirements and distribution. There are also caching options that you have in CRL and OCSP responses that enable you to push that out to gateways or other components of your network. And it really depends on some of the details of that infrastructure and architecture, what is going to work or where the constraints or requirements are. But there's a number of options and opportunities we have for how those trust decisions are being made between the different actors in the ecosystem.
Great, thank you, Lancen.
Thanks.
This next question is a quick question for James. Is Intel Quark supported?
Yes, we have run on an Intel Quark platform.
Quick question with a quick answer.
Yep.
James, while you're still, while you're still on fire here, can an infrared or some special camera be used to read the contents of the SRAM PUF when it is powered?
Great, that's actually a good question. We have, part of our certification process, we've had to go through very extensive testing, both by the users of the technology and by third-party labs. So inside of those third-party labs, there's been a lot of equipment that has been thrown at breaking our technology. To date, none have been successful. Examples of equipment that were being used are things like focused ion beam, scanning electron microscopes, photo emission analysis. All of those tools applied to our technology has not netted any evidence of the key. And it's important also to note that this isn't just one function of the SRAM. It's a combination of the function of the SRAM plus our algorithm. So there's a couple of layers of reverse engineering that would have to be applied to even get to a useful bit of information, and even then potentially only valuable for that one device. So you don't break one and break all. But so with the use of special cameras and all of the different equipment that's been thrown at it so far, 0 breaks of our key.
Great, thanks, James. We do have a couple more questions, and then we're gonna have to wrap up. This one's going to be geared towards Lancen. Are there limitations to the type of devices that you can install a digital certificate on, and does the device need a certain baseline level of computing power?
Yeah, it's a recurring question that we definitely see, and unfortunately at this stage there's not a blanket answer. As with a lot of things, it really depends, because it depends on the scope of the other applications that are going to be consuming computing and resource power and storage on the device. But at a general level, I mean, when we use PKI, we expect that the device has some capabilities for internet connection, that it's potentially using some type of TCP/IP library. And oftentimes, one of the easiest places to apply PKI and certificates for authentication is within a TLS handshake, but that's not the only one. So those are some of the requirements that we see in there. But the good thing, and one of the strong benefits over PKI in conjunction with a secure key generation and storage mechanism like SRAM PUF, is that it can be applied into a wide range of chip architectures and subsets of systems. So there isn't, a blanket answer, and there are also, considerations over the crypto algorithms that are going to be used to support. For example, ECC is a key algorithm that we can use on more constrained and embedded devices that has less CPU resource requirements and storage requirements for the keys that are generated in that scenario. So.
Great, thanks again, Lancen. I think we have time for 2 more questions. We do have a bunch more coming in. We can answer these ones offline, but let's position one more to James and one more back to Lancen. James, have you done any reliability testing for automotive?
Yeah, that's a good question. So reliability is a big concern when you start talking about core security, root of trust, things like that. We have done testing for the automotive industry. That was kind of a subset of the testing that we already do, especially when we look at military and government applications that go even deeper sometimes than the automotive requirements. So in our reliability testing, we cover from -50 to +150C. We cover from voltage swings from plus or minus 20%. We have done the testing analysis across 25 years. And then you look at environmental conditions like humidity and other functions. So we have done the testing inside of all of those areas. So right now, our lifetime of plus 25 years is higher than typical applications of secure storage. So if you look at OTP, you look at flash, our technology running inside of the SRAM actually has a longer lifetime cycle through all of its testing than the other storage methods for securing keys. So we can get into more details if that was a specific question for somebody. We'd love to answer that on what we've done specific to the automotive field. But like I said, that was a subset of our overall testing that we've had to do both for the secure payment industry and for the government and defense space.
Great. We have time for one last question. This one is more geared towards Lancen. Does certificate provisioning have to happen during the manufacturing process? Can you install certificates on devices already in use? Also, what about renewing certificates in the field? How does that process work?
Yeah, it's definitely another recurring theme and question I think that we see here, and the short answer is it can really happen at almost any stage of the device's life cycle. The more trusted or the more secured, I think, approach and solution that we do recommend is building those roots of trust as early in that device or component manufacturing process as possible. As James kind of covered in that workflow, it's potentially possible from the semiconductor or silicon manufacturer into the OEM life cycle. The other dimension of it is how that device actually operates in the field and how the identity credentials are being updated or published during that device life cycle. And there are definitely a range of options that both GlobalSign and Intrinsic ID can assist with in that area. There are unique protocols that we are able to offer, as well as standard protocols too, that help enable those enrollment requirements and environments as far as how those devices reprovision their identity in a trusted manner. I guess, James, you might have some comments too over the life cycle. I'll give you an opportunity to feed in on that one as well.
Yeah, thanks. It's very similar. I'll echo the same things that you were saying, which is root of trust being very important to develop as early in the stage as possible. But that doesn't mean then if you didn't design for security at that first stage that you should forget about security. And that's part of what we offer with the software version of this, is that if you still want to get into the area where maybe you're looking at meeting the Department of Homeland Security standards for hardware-based security, hardware starting of that security function, we could still do that in a software implementation. So we still drill down to the SRAM for the hardware source of entropy. So the rest of the functionality can happen after the fact. So while we would like everybody to be thinking about it at the very start of their design cycle, if they have some products that have now found their way into a field where they're at risk end nodes, we could still apply security to them that meets the security standards and recommendations. The other part about that is that the interesting thing with a software implementation for a root key like this is that you could make adjustments to this down the road. If you needed to address for a security algorithm or something that had been broken or is in question, you could make updates to that device out in the field. So there's a lot of interesting things that can be done with this technology that helps these devices, especially if they're going out for long life cycles, 10, 15 plus years for smart meters out there. What do you do to plan for security updates for them? And with the combination of a SRAM PUF root technology and then a public key infrastructure methodology, you can do a lot of things interesting throughout the entire production flow or even then out in the field.
All right, great. Thanks, guys. We do have some additional questions that we'll field in an email fashion. We've basically come to the end of today's webinar. James and Lancen's contact information is up here on the last slide. Feel free to reach out to them if you have additional questions or would like to start to talk about even a proof of concept. Once again, thank you to everyone for attending today. I think we had a really great webinar.